I will remind everybody of the exemption policy because you can exempt the final. So if you do not have more than 4 absences in this class, which hopefully you don't, most everyone comes. If you don't have more than 4 absences in your advisory class, that 6th period class you have on Tuesdays, if you do not have more than 6 absences more than 4 absences in 6th hour and no more than 4 in this one, that's a good start. You can't have any missing assignments at all. No missing assignments. And your grade has to be at least a 75%. And no fines or fees, but we don't have fines or fees in this class. So if you can meet those qualifications, you can be exempt from taking the final and be done a week early in this class. It would be fabulous. That'd be a great thing. So that's always exciting. So strive towards that. If you got any missing assignments, get them turned in. You don't want to have to take the final. It's like you haven't been absent. You haven't been absent advisory. Your grade's over 75. Oh, but I didn't turn an assignment back in module 6. Oh, you don't want something like that to make you have to take the final. You want to get everything turned in. So let me see what else we got going. Well, we do have half of us here now. One of those Mondays. It's not summer yet, guys. You still got to come to class. I know. We get excited. All right, let me see. So counting the 5 people that aren't here and 8, we're just missing 3. I guess that means we can get started on that. So I think what I'm going to do is I'm going to just look and see what we're studying, and we're going to do some of this on paper because I just want you to have a good understanding of it without getting confused with how the lesson presents it. Sometimes they get a little bit wordy or we can't always figure out. I know they got a couple of videos where they explain this, but we're going to go through it ourselves where we can get a little better understanding, I think, on paper. But let's take a look at what we're supposed to be doing this week. Okay, if you guys are not using the grade screen in Buzz, you're missing out. I go to this grade screen at the start of every class on purpose because if you are trying to figure out, I think I'm missing an assignment, you may be able to see that in Hack, okay, but it's easier in Buzz to just go to this grade screen. And if you see any zeros, that's a missing assignment. And it's easy to tell which assignment it is. Just follow the 0 over. You need to go do that assignment. So if you're trying to be exempt here at the end of the semester, and if you have missing assignments, you have to take the final. But if you don't have any missing assignments, you can be exempt. So if you're trying to figure out, am I exempt? Well, I'll email you if you're exempt. But if you're trying to figure out if you have missing assignments, go to the screen right here in Buzz and look to see if there's any zeros. This week we just have 7, and I just added this lesson. I was going to skip this, but I'm like, well, we need another week, and you need to see this. This would be good for you to see. Sigma notation, because it comes up a lot when you get into college. You see this a lot in higher math, and it's not complicated, but if you haven't seen it, you're like, what in the world is this thing? It's a Greek sigma. So we're going to look at that sigma notation. 7.07. And like I say, I'm gonna put it up here, but I think I'm going to switch over first, and we're going to look at this on paper before we look at it on there. So this is still dealing with arithmetic series, just like we have been. Arithmetic sequences, arithmetic series. And let's say that we're just going to make one up. 2 plus 5 plus 8 plus 11. Okay, and we want to add the first 6. First 6 terms. Which again, this would be pretty simple, right? Oh, focus, pay attention thing. This would be pretty simple because it's small numbers, but we're going to use this just because you can use it with bigger ones too. I'm just showing you how this works with something small and simple that we can handle. So if we were to write the formula for this, we have this a sub n, a plus 1 So, well, if we did S sub 6, but our formula would be, it's A sub 1, which our first term is 2, plus the common difference, well, that goes up 3 every time, times n minus 1. 2 plus 3 n minus 1 is our sequence right here, and we're wanting to sum up the first 6 terms. Well, in sigma, let's simplify this first of all. 2 plus 3n minus 3, that's just distributing, which means this is just 2 minus 3, negative 1 plus 3n. And we want to sum the first 6 terms. Well, in sigma notation, here's this thing called a sigma. That's a Greek letter, the sigma. And we can say the same thing as this, negative 1 plus 3n, but we would do it this way. N equals 1. That means start with the first term and make it go all the way through 6. So in sigma notation, this is the same as this. But instead of an S, we use this Greek sigma. And we say n equals 1 to 6. That means we start with the first term and we add them all together all the way to the 6th term. And the way you do that, and like I say, this one would be real easy to do without this, but I want you to see how the process works. So if we were doing this sigma from n equals 1 to 6, we would say, okay, the first term would be negative 1 plus 3 times 1. All right, that would be when n equals 1. And then we'd go through it again and we say, okay, now equals 2. So that'd be negative 1 plus 3 times 2. That's the second term. Plus, then we do negative 1 plus 3 times 3 plus, two parentheses, negative 1 plus 3 times 4 plus negative 1 plus 3 times 5 plus negative 1 plus 3 times 6. And we would stop at 6 because that's the first term, second term, third term, fourth term, fifth term, and sixth term. Then we could just simplify that. Negative 1 plus 3 times 1. Negative 1 plus 3 is 2 plus, and we know what they are up here, but if this was a more complicated one, this would work the same way. 3 times 2 is 6, minus 1 is 5. 3 times 3 is 9, minus 1 is 8. 3 times 4 is 12, minus 1 is 11. 3 times 5 is 15, minus 1 is 14. And then it's 18 minus 1 plus 17. And then we would just add those up. Be 7, 15, 26, 40, 57. So it equals 57. So that tells us that this equals 57. Now you're saying to yourself, and I know you're not saying this aloud, why in the world would I write it like this when I can just do this? Well, sigma notation allows something that this doesn't. Because we could say, okay, I'm going to use this same sequence, negative 1 plus 3n, but I'm going to say start with the 4th term and go through the 9th term. Well, that's different. That's why we use sigma notation, because this would say we don't care about the first 3 terms, right? We don't care about those. Start with this term and add all the way up to the 9th term. And we would do it just like this. We go negative 1 plus 3 times 4. That would be the 4th term. See, we'd start with whatever n, and then we would add that to negative 1 plus 3 times 5, because now n would be 5. And we would keep going like that all the way until we got negative 1 plus 3 times 9, which is our last one. But we would do all the terms in between there, and then we would calculate that and add that up. So that's how sigma notation differs from this, and that we don't have to start at 1. This one says the first 6 terms, 1 through 6. That's it. That's all we can do. But if we write it with sigma notation, that gives us a different way that we can tackle a problem. So that's what you got to pay attention to. It may not be the first term that you're starting with in sigma notation. All right, let's see what Buzz has as a lesson for that. Oh, maybe they should make iMath. Steve Jobs was a co-founder and CEO of Apple Incorporated. He would stand up in front of the world and tell us why we needed his new product, and the world would listen and they would buy it like crazy. It seemed that no matter what it was, if he was telling you about it, you wanted it. In mathematics, there was a guy similar to Steve Jobs. His name was Leonard Euler. Now, he was born way back in 1707, so he's not around for the internet age. Now, don't get me wrong, Euler was not promoting iPads or iPods back in the 1700s. No, Euler sold the ideas and notations for some of math's advanced concepts. Even if he didn't come up with the concept, he sold everyone on this is how we should write it down. This is the way we should note that in mathematics. Like, he's the one that came up with using I for an imaginary number. That was Euler's idea. Using this symbol here to represent pi. That was his idea. Pi, they'd already figured out pi was a number, but he's the one that said, let's use this to represent pi. And he's the one that said, let's use f of x to represent a function. And e, he's the one that came up with using e to represent that number e that we use. All that's Euler. Euler contributed a lot in mathematics. A lot of stuff he came up with the new theories, but other stuff he just figured out, let's all use the same thing to represent that so that we all understand what we're talking about. All right, so we're going to learn how sigma notation is used to evaluate a series. And let's see. I guess we can watch this video. It's probably going to cover what I just did on paper. But maximize that. It's just 2 minutes. Like I say, it may cover what I just did on paper. I don't remember for sure, but we'll see.
Let's examine the sum of the first 6 terms of the arithmetic sequence 3, 7, 11, and so on. From this information, you can determine that 3 is the first term, a sub 1. 7 is the second term, a sub 2. 11 is the third term, a sub 3, and so on. To describe this series using sigma notation, follow the Greek sigma symbol with a sub n, which indicates the various terms in the series. The variable n is used to indicate the changing subscripts of each term. Since the series begins with the first term, n equals 1 is written underneath the sigma symbol. This is known as the lower index. This series ends with the sixth term, so 6 is written above the sigma symbol. This is known as the upper index. Therefore, the sum of the first 6 terms of the arithmetic sequence, 3, 7, 11, and so on, can be represented by this sigma notation. Another way to represent this sequence, using sigma notation, is through the use of an algebraic expression. Recall the formula for finding any given term of an arithmetic sequence is a sub n equals a sub 1 plus n minus 1 times d. In the sequence 3, 7, 11, etc., the first term, called a sub 1, is 3. And the common difference, d, is 4. Substitute these values into the formula and simplify. The sum of the first 6 terms can now be represented by the summation of -1 plus 4n from 1 to 6.
So you see what they did there? Ended up with the sigma notation. They basically went through the same thing I did on paper, just using a different sequence. So that is the first 6 terms. And then here's how they fill them out. When n equals 1, you substitute 1n for the n in that same -1 plus 4n and work out all that and end up with 78 in their sequence. 3 plus 7 plus 11 plus 15 plus 19 plus 23 equals 78. Which ends up the same thing as using the arithmetic series formula, n divided by 2, then a1 plus a sub n. You end up with 78 as that as well. So, all right, here's page 2, which there's only 2 pages of this lesson. And it says, okay, here's where I talked about where sigma notation comes in a lot of times, where we don't have to start with the first term. All right, let me do this real quick. This is 5 minutes because he getting a little more detail on this.
We're going to look at sigma notation for arithmetic and geometric series now. On the left here, I've got an arithmetic series. That is one where we're going to add something to each term to get the next term. Okay? And in this case, this represents the number of students who are graduating from our high school. Okay? And what it does, it starts off in the first year at 500 students. But then we're going to add 10 students each successive year. You can see the first year when n equals 1, we get 1 times 1 is 0 times 10, so we don't add any. But then the next year we're going to add 10, next year will be 20 more, next year 30 more, okay? Now, what we have though is a problem, because our records vault currently only has room for about 7,500 record folders. And every time we have a student graduate, well, we have to put that record folder somewhere. So what we want to do is we're anticipating this 10 years or 10 students growth each year. And we want to look at the next 15 years, because that's about how long we think our high school is going to last before we have to build another one. And we want to make sure we have enough room in our records vault for all of those records folders from the graduates we're going to have. Now, we could go through and calculate each one of these steps, 15, one at a time, and then add them all up. But a much faster way to do it is to use a sum formula for an arithmetic formula, which is n over 2 times a1 plus an. All right? Where a1 is your first term, an is your last term, and n is the number of terms. Since it's 1 through 15, n is going to be 15. a1, we plug in n equals 1, and we're going to get 500. an, we're going to plug in 15, and we're going to get 640. So let's plug those numbers in and see what we can find out. So 15 over 2 times 500 plus 640. Okay, and we add this up and do the math, and what we're going to find out is that we have 8,550. I guess maybe we're going to need to expand our records vault a little bit. Okay? But this is a very simple way to add up a long arithmetic series without having to do every term. All right, now here we have a geometric series. And this is one where each term is some given multiple of the previous term. And in this case, what we're talking about is cell phone battery life, something near and dear to all our hearts. Now, this cell phone battery starts out with an 8-hour life. You charge it up to a full charge, it'll last for 8 hours. Hey, not too bad. But what I know about batteries is every time you charge them, they go a little bit less. So in this case, we've put in a multiplier of 0.95. Our common ratio is 0.95, because what we found out is on our battery, each time it charges up, it only charges to 95% of what it did before. So we're going to look at what happens after about 50 charges. Okay? And in fact, we're going to look at how many hours we're going to get out of all 50 charges. Now, if they got 8 hours on each charge, then we would have 8 times 50 would be 400 hours. Not too bad. But let's see what we get here with this geometric series where it's going down by a certain multiplier each term. So if we plug in here and calculate, what we're going to find is, well, let's see, our sum formula is a1 times 1 minus r to the n over 1 minus r. All right? a1 is our first term. We plug in n equals 1. This goes to 0. This just becomes 1. Anything to the 0 power is 1. Times 8 is going to be 8. Okay, so a1 is 8. R is our common ratio, which is 0.95. So we're going to put in 1 minus 0.95 raised to the n power, which in this case is going to be 50. And then we're going to divide this whole thing by 1 minus r, or 1 minus 0.95. Now if I put this into my calculator, because I'm too lazy to do the math myself, I will find that S of 50 is going to be about 147.7 hours. So you see that multiplying by 0.95 each time has had quite an effect. This isn't quite the 400 hours we were hoping to get out of our battery. But that's the way things go.
He talked about using the formulas that we know when the problem, even though the problem is in sigma notation, and this is arithmetic sequence on the left, and this is a geometric. So you can use the sigma for a geometric sequence just the same. So even though if we have it written like this, we can go back and use this formula over here. It's easy. Remember, we have the arithmetic series formula back at our notes. And we also have the geometric series formulas. So just because it's presented in this, you don't have to do all of this if you want to switch back and use this formula, but just you have to know how to read it. That's what it's all about. It's all about how to read it. So these are the same. So that's just like if we have y equals 2x, that's the same as f of x equals 2x, right? It's just a different way of writing the same thing. These are the same, and these are the same. So that's all that we need to know. Just know how to read this, and then you can use a different formula if you don't want to do each term one by one, because that gets kind of tedious, especially if you're doing from 1 to 50, as he was doing in this video. But look at this example they have here. Here's a sigma n equals 2, and it's got 5 on top, the upper level, 2n minus 3. So this one, they do it term by term because we can't use our sum formula, because our sum formula adds everything from 1. So it turns out this is 16. But there's some examples here. This says, given this sequence, 8, 3, negative 2, evaluate n equals 4 up to 7. So you're doing the 4th, 5th, 6th, and 7th term of this arithmetic sequence. And it'll go through and show you how to do that. If you try it on paper, see if you can do that, and then check to see how they did it. And you can also do it geometric, as he showed in the video. You can also change the expression from arithmetic to a geometric. Remember, and there's what the geometric sequence looks like: a sub 1 r n minus 1. And there's the lesson summary. That's the end of the lesson. Upper limit, lower limit, the expression. And this just says find the sum starting at this term and going through that term. So don't get confused by that. There are 2 pages of practice problems. If you need more practice with it, if you're like, I'm not sure I understand, Mr. Brock. Well, great. That's why we have practice problems. So you can find the sum. Here's one that you take the first 4 terms. Starts at 1, goes to 4. 1, 2, 3, 4 of this. Which one of those is it? 6 problems right there for you to practice. Then when you go to the next page, here's some more practice problems for you. This has find the indicated sum. Evaluate n equals 1 to 5, the first 5 terms. And this is a geometric sequence. Look, it's 3 times the common ratio times n minus 1. And then you can check your work here and see if you got the same thing they did. But there's 3 problems there. All right, let's look at the assignment that goes with this week with this sigma notation. And again, you can use the formulas we already know, but if you don't know how to read this, you'll struggle. Let's see, evaluate sigma n equals 1 to 12 of 2n plus 5. This one, oh, look, you start at n equals 2. So from 2 to 10, what does that add up to? Now you could take it from 1 to 10 and then subtract the first term off if you can calculate the first term. This one's the first 5 terms of this sequence and 2 to 10 of this geometric sequence. And last problem, given this sequence, determine the sigma notation to find the sum of terms 4 through 15. So this, you're trying to figure out which one of those representations actually represents this sequence, terms 4 through 15. So a little reverse action on the last one. But that's it. 5 problems on sigma notation. Something just a little bit different than we've done before, but really it's just another way of writing what we already know with the arithmetic sequences, geometric sequences and series, all of that. So not too bad. Next week, we're going to test over this unit of the arithmetic sequences, geometric sequences, all of that. We'll test next week. I was going to test this week, but I'm going to push it back one more week and show you sigma notation, because you see it all the time in math. You open up them big fancy math books, you see this sigma notation all the time, and you're like, I hate for you to get through the year and have no idea what that is. All right, guys, that's all I got for you this week. This is an A day Friday, so I'll be here Wednesday and Friday. If your grade's below 70%, and there's hardly anyone that is in this class, you guys are doing fabulous. If you have any missing assignments, get those turned in so you'll have a shot at that exemption, unless you've been absent a bunch of times. But we'll see you guys Wednesday or Friday. If you want to come and ask questions, I'll be here. So I'll be here Wednesday, Friday. Otherwise, we'll see you next time. I did eat. Ow! What? I just need a ride. I just wanted a little ride. That's all I needed. Come on, Big D. Come on.